today's topic is Biot-Savart's law. Now, this is one of the two very powerful laws in electromagnetism. So, moving charges and magnetism is also called as electromagnetism. It's nothing but the production of magnetism or magnetic fields from moving charges. So, that's simply in short, simple single word, it's called as electromagnetism. So, there are two very powerful laws in electromagnetism. Now they are as powerful as the Gauss law in static electricity. Also, Gauss law, not just a very powerful law in static electricity, almost in the entire electricity, it's a very powerful law. So like that, two laws are there. Actually, Gauss law exists even in electromagnetism. Also, Gauss law exists, but Gauss law is not so useful as the Gauss law in electricity. Coulomb's inverse square law, we have seen that it exists in electricity and also in magnetism. In electricity, whatever quantity exists, similar quantity exists in magnetism, like electric field vector capital E, magnetic field vector capital B, like that. So Gauss law exists really both in electricity as well as magnetism, but in magnetism it's found to be not much useful. So very powerful laws useful in electromagnetism are two laws. So one of the two laws is the Biot-Savart law. Next is Ampere's law. Ampere's law is somewhat similar to Gauss law but slightly different. So Biot-Savart law is the first very important, very powerful law in electromagnetism. So this, it's actually a 4 marks topic. That means a short answer question. It's a small derivation. So carries 4 marks. So now Biot-Savart's law, it's actually deals with the magnetic field due to a current carrying tiny element. So this is also called as magnetic field. So this magnetic field, now magnetic field vector symbol is B. So this is the magnetic field due to a very tiny element. So this is a small magnetic field. So this is denoted as a dB. So capital B denotes a regular magnetic field, normal magnetic field. dB, like dl, denotes a very small length, tiny elemental length. Like that, this is an elemental magnetic field. So the magnetic field due to a very tiny current carrying element, dl. So regular length of a conductor is denoted as L, a tiny element, the tiny length of a small portion of a conductor is denoted as dl. It's simply called as current carrying element. So due to a current carrying element. So Biot-Savart's law actually gives an expression for this particular magnetic field or magnetic induction field dB due to a tiny current carrying element. So current carrying element symbol is taken as dl. So I'm just writing it as dl. So I'll just make it a little more clear. So dl. So L stands for regular length, normal length. So dl stands for a tiny, extremely tiny length. So this is the other way of writing the same side heading. So the topic 4 marks short answer question. It's very important in every board exam, almost throughout the world. So carrying about slightly less marks than a regular essay question. Regular essay question carries 5 marks to 8 marks. So this carries about 4 marks. So anyway, it can be given state and explain Biot-Savart's law or derive an expression for magnetic induction due to a current carrying element. That way also it can be given. Now consider a tiny current carrying element. So now consider firstly a regular shaped conductor, a wire. It need not be a straight wire. So previously Oersted's or Oersted's experiment, we have seen a straight current carrying conductor. So Oersted's experiment also is very useful here. So already we have seen the diagram of the Oersted's experiment. It was something like this. So just try to recollect the diagram of the Oersted's experiment. So I'm just drawing it roughly. That's very useful here also. So firstly, a plane is taken, a horizontal plane. It's like the plane of a cardboard. So this is a horizontal plane. Exactly perpendicular to the horizontal plane, passing to the center of this cardboard, a rectangular cardboard, say horizontal rectangular cardboard through the center. A long current carrying conductor is considered, which is carrying a current I. This is a very, very long. So exactly speaking, infinite length. So because of this current carrying conductor, now when current is flowing through this conductor, we have seen that a magnetic field is established around the current carrying conductor in this plane. That means in the plane perpendicular to the length of this infinite conductor, infinite straight conductor, the magnetic field will be such that the magnetic lines of force are exact concentric circles this way. Exactly concentric circles. All these circular lines of force, they have a common center. The center exactly coincides with the point of intersection of the conductor with the plane, which is perpendicular to the conductor. So the direction of the lines of force is actually given by the, we have already seen that it is given by the right hand thumb rule or right hand corkscrew rule. It's given simply by the right hand thumb rule or the right hand corkscrew rule. So that is actually very useful here, even here also. Now this is for a long, infinite long straight current carrying conductor. So magnetic induction at any point is denoted by the regular symbol B. But now consider not just a fixed shape straight conductor, but it can be of any shape, a general shape. So general shape, I'm just taking it as like this way, any shaped conductor. So this is carrying any some current this way. It's carrying a current this way. The strength of the current is denoted as I. So always for a single conductor, the strength of the current at every point will be same. So here it is I means everywhere it is I. So now consider a small elemental length in this entire conductor. A tiny elemental length, extremely small elemental length. So from here to here. So it's so small that this elemental length is denoted as dl. So already we have seen that dl stands for a, so dx is what? Differential of x. Dx, dy is what? Differential of y. It actually stands for a small change in x. So like the dl also can be taken as a small change in length, or really it can be taken as a small length also. Both are one and the same. Both a small change in length or a small length, they are one and the same. How they are one and the same? This is very, very important in while using differentiation, derivatives and integration. Why change in length and small length are one and the same? It can be taken like this. Now from here to here, so let this be the bottom end of the conductor. So from here to here, let the length of the conductor be L. Now let this length be slightly increased by a small value up to here. So from the bottom end of the conductor, imagine that it's ending up to at this point, the lower end of the conductor here, where is ending here. So from here to here, the total length here up to here is L. So when we are considering a slightly more length, it will be L plus a small increment in length. So length from here, it's at some value. Now we are increasing the length further, slightly more length. The small length is denoted as dl. It's also nothing but slight increment in length or slight increase in length. So that way, this can be taken as a change in length. So up to here length is L1, up to here length is L2. So increase in length is what? L2 minus L1. So this can also be taken as a small portion of the conductor. So it's a small length dl. So dl can be taken as a small length or it's a small change in length. Both ways it can be taken. So there's not much. So this is how the concept of differentiation and integration are used whenever we are considering a small value of a quantity. This is also a small value of the magnetic induction, or it can also be taken as a small change in magnetic induction. So both can prove to be one and the same. So any doubt is there, think a little here. Stop for a moment and think about it. It can be really seen that both are one and the same. So this is a small elemental length. So this small elemental length is denoted as dl. It's simply denoted as dl. So now through this dl, only current I is flowing. Now because of this current, now charge is flowing through the conductor. Whenever charge is in motion, already we have seen Easted's experiment. Whenever charge is in motion, which actually nothing but flow of charge or moving charge forms an electric current. Always a magnetic field is created. So due to this current carrying element also magnetic field is created at any point. So take the point somewhere here. So at this point, say call the point as P. A magnetic field will be created here. So this magnetic field, because it's a small elemental length, field also will be very small. Now this being a vector, it can also be known as dB bar. Now that is what is actually required here. So now, now consider a straight line joining the point P to the center of the element. So I'll just draw a straight line. this way, point P to the center of the element. So this length of the straight line is nothing but distance of the point P from the center of the element. It can be taken as R. This can be taken as R. Now taking the center of the element as origin O, OP can be taken as position vector of the point P with respect to the center of the element. Now the very important thing is through this element, now this is a small length dl, it's a small change in length. It can also be taken as differential of length also. So what is the meaning of differential of x? It's nothing but change in x. It's really nothing but, exactly speaking, it's nothing but change in x which is tending to 0. It's very small. It's the smallest value imaginable but slightly bigger than 0. So that is called as differential of x. In short, it's called as differential of x. Whenever change in x tends to 0, delta x is tending to 0, delta y is tending to 0, it's simply called as differential of x or differential of x. So this is the differential of length. So how small it is means it's unimaginably small. So very small portion of a curved conductor or a curved line also can be exactly taken as an exact straight line. So this elemental length can be taken as an exact, almost exact straight line. So exact straight conductor, already we have seen that the lines of force are concentric circles. So now for this exact elemental length, a straight elemental length dl, what is the magnetic induction dv? That is what is actually required. Now through this elemental length, charge is actually in motion. Now consider a very small amount of charge here. Now very important thing here, the vector concept can be vector concepts and vector properties are actually used here. Now the vector properties, all the properties of vectors are very simple. The basic thing about a vector is it has, along with magnitude, it has a direction also. And more important than both is a vector quantity obeys the parallelogram law of vector addition, obeys the exact parallelogram law of vector addition or the triangle law of vector addition. And based on parallelogram law of vector addition, very important property of a vector is a vector can be resolved into two components or two or more components, a horizontal component, a vertical component, or an x component, a y component, or x component, y component, and z component. That is another very important feature of a vector quantity which is actually directly obtained from the parallelogram law of vector addition. Now a charge, a small amount of charge. So the elemental length I'm just taking here. It's very simple. So because this is the elemental length, so I'm taking this in the rough column. So whatever concepts we are actually applying here in the actual syllabus topic, the concepts belong to the previous topics. Now here we are just using the concept of vector, parallelogram law of vector addition or resolution of vector into its components. And another thing is even the Oersted's or Oersted's experiment also, it actually belonged to the very first topic of this particular lesson, moving charges and magnetism or electromagnetism. So this is, I'm just writing this particular whatever concept we are using here for this topic. I'm just showing it in the rough column. The same way here also I'm just showing in the rough column. Rough column things, topics or rough column concepts, they can't be taken lightly because they are the basic laws. They are the basic scientific laws. They are the basic scientific definitions which will be useful in the derivation. The derivation will be just completed here. But the definitions and laws which we are using here to get the derivation of that particular topic, the same definitions will be again and again used almost each and every topic beyond this lesson, beyond this topic, and beyond even this lesson or beyond even this particular subject when you go to higher classes. So the rough column steps are actually, strictly speaking, they are more important than the actual derivation. They are just, derivation is just an application of the simple definition, scientific definitions and scientific simple laws of the previous lessons. So now this the elemental length, it's simply taken as dl. So this is the elemental length dl. Now through this elemental length from here to here, because it consists of moving charges, let the total charge present in this elemental length be denoted as dq. It's actually moving with a velocity. It's actually moving with a velocity like this. So velocity, so I'm just showing the motion. Velocity need not be exactly shown separately. The reason is the direction of current itself is the direction of velocity inside the elemental length. So there is a velocity also here. So now multiply the velocity, multiply the elemental charge, small elemental charge with the velocity. So charge into velocity. Now this quantity, velocity being a vector, charge being a scalar, scalar into vector will give a vector. It's exactly like mass into velocity. Just see here, this is comparable to mass into velocity. Mass, scalar quantity or scalar quantity, Velocity is a vector quantity. The product is what? Momentum. So the direction of this vector quantity is taken to be in the direction of this new vector quantity obtained by multiplying scalar and vector is taken to be in the direction of velocity. And it, more importantly, it obeys the parallelogram law of vector addition. Velocity obeys parallelogram law of vector addition means we know the parallelogram law of vector addition. In just one equation, entire law can be remembered. What is the resultant vector? R is equal to square root of p square plus q square plus 2p cos theta. P and q are the two vectors added up to get the resultant vector. That's the basic equation for the magnitude of the resultant. And the statement of the parallelogram law of vector addition also we know thoroughly. So velocity obeys parallelogram law of vector addition. It actually resultant is given by that particular equation. R is equal to square root p square plus q square plus 2p cos theta. Based on that equation, you can prove that when a scalar quantity or any number is multiplied with a vector, the new vector quantity obtained, like here momentum, also obeys the parallelogram law of vector addition automatically. It has to obey that equation. That means it obeys the parallelogram. So like that here also we are getting a new vector quantity. This is called mass momentum. This is simply called as charge momentum. It is simply called as charge momentum. And it can be proved that this charge momentum, very important thing is charge quantity is there and motion of charge is there. But charge and motion, what is the quantity related? Current is actually related. And it can be proved that by using simple equations, it can be proved that this is exactly equal to current into the elemental length. Now this is a very important step which we'll never be using in the derivation. But any doubt comes in the derivation, the basic definitions will be helping us. Now this is the very simple definition. So current into elemental length is simply called as, in short it's called as usually current element. It's simply called as current element. So best way to remember this is, it can be remembered as charge momentum. So charge momentum. So I don't want to write that because it's becoming very congested. So you can just remember it. This is mass momentum. We know this mass momentum. Now mass density is mass per unit volume. Weight density is weight per unit volume. Charge density is charge per unit volume. Like that. This mass momentum. This is charge momentum. So this can simply prove to be equal to I into dl. Just you try to prove this. It comes. I just give a small hint. So dq, let total time taken by the charge dq in this elemental length to move from this region completely, to move away from here to this is the tail of the charge dq, this is the head of the charge dq. So for this entire charge element to move out of this region, it takes dt time. Then just see here, charge into velocity. So distance traveled by a part of this charge element, every part of this charge element can be proved to be dl. So velocity is distance by time, dl by dt. So dq by dt. So dq is the charge which is flowing out out of this particular region. That means out of this cross section in time dt. So v is dl by dt. dt take here. dq by dt is what? Current. Charge flowing divided by time is current. Current into dl. dl, that is idl we are getting. So in just one simple step, one and a half steps, we are getting this particular thing. So the important thing now is very important thing now is what? This is a vector. Charge momentum is a vector. So here we can't take current as vector. So actually this can also be expressed as, just you try this also as a practice. You just try this also. This can be expressed in terms of current vector. It's called current density, j bar dv, where dv is the volume of this elemental length. So area of cross section also will be coming here. This also in just one step you can just try to prove it. As a practice you can just prove it. So the most important thing now is, here we can't denote I as a vector. So here elemental length is treated as a vector. So what is the direction of this elemental length? Same as the direction of velocity, means velocity direction is same as the direction of current. So this is the vector representation of the elemental length, IDL bar it's called as. Now the most important thing here is, now here we have a vector here which is actually really charge momentum, which is dq into v. So which is nothing but current element IDL bar. So what is the direction here? This is the direction. I'm just extending this here. So I'm just drawing a tangent here. Just observe here, very simple. So I'm just drawing a tangent here to the exactly at the center of the elemental length. So this is also in the tangent direction only, the elemental length can be clearly seen to be present. Now the most important thing is, along with this, now this tangential direction can be taken as the axis of the elemental length. Now very important thing is, along with this can also be called as, just like a bar magnet axial line of a bar magnet, axial line of electric dipole, equatorial line, like that. This can be taken as the axial line or simply axis of the elemental length. And along with the axis of the elemental length, we can take a perpendicular bisector, exactly like the equatorial line of a bar magnet, or exactly like the equatorial line of a electric dipole. So now this is the perpendicular bisector. Now very important thing is, already we have seen that a current carrying conductor, or even more simpler way, a moving charge produces a magnetic field. Now inside the conductor there's a moving charge. That moving charge is producing a magnetic field around it. So if it's an infinite conductor, the magnetic field is completely symmetric in the form of concentric circles. Even if it's a point charge also, there is a magnetic field around it. So which may not be exactly concentric circles, but somewhat similar to that, it will be present. Now the important thing is at different points. So for an infinite conductor, at each and every point, it is in the form of concentric circles. So here we can draw another plane like that. But for a point charge, it will not be so simple. But in certain ways, certain positions, it will be almost exactly similar. At certain, for example, if we take exactly the perpendicular bisector for this elemental charge, so like treat dq as a point charge, it can be shown that on this perpendicular bisector, exactly due to this point charge, treating the elemental charge as a point charge, it can be shown that it's exactly concentric circles, but not at other points due to this charge. It will not be exactly concentric circles. We can just check this later whenever you get a time. So all these such things you can just try to prove them. So actually, there is nothing more powerful than a scientific derivation. Problems are very good. They are just applications, but not much thinking is required. The moment we get the answer, we'll be getting satisfied. That's not sufficient. Each and everything you have to question, and for each and every question there is an answer. All answers in science and technology are based on very simple definitions and very simple laws or principles. Only few principles or laws will be there in every lesson. Only one or two laws will be there, see. And definitions also, only three or four definitions on such things only. See here, many things we are getting directly based on the simple definition of a vector quantity. It's a quantity having both magnitude and direction that does not end there. Continuation is and obeys the parallelogram law of vector addition or the laws of vector addition. So that such definitions we are getting new things here. So now the important thing is, on the perpendicular bisector of this elemental length, there is a magnetic field. There is a magnetic field here, and that magnetic field, it is it can be proved that it has been proved that it is exactly proportional to the current element dl, ideal current element, which is actually what is a current element, which is nothing but charge momentum, ideal. It's a vector quantity. On the perpendicular bisector only this is found to be exactly applicable. Then what about that? Means a magnetic field is created on the perpendicular bisector and which is proportional to ideal. That means if ideal is doubled, magnetic induction also will be getting doubled. You also can just try to prove it. Roughly we can get the proof just in a few steps, but little thinking will be required. It will not be so complicated. And very important thing is, on the axis, what is a magnetic induction? That magnetic induction is found to be exactly zero. No field will be established on the axis. So in whatever direction the charge is moving, or point charge or elemental charge is moving, in that direction, both whether it is forward or even backward on the axis, field will be completely zero. But on the perpendicular bisector, exactly perpendicular direction of the velocity or perpendicular direction of the elemental length, which is a vector ideal bar or charge momentum dq into v, perpendicular direction, magnetic induction will be there, and that will be maximum. Now, what about in between? It will be lesser. So gradually from here to here, it can be shown that it decreases and finally it will become zero. Now, why this happens? The reason is the charge momentum or elemental length ideal bar, or simply, now I'm just not taking the vector nature here. Vector equations are complicated because when you're writing vector, you're showing vector nature in an equation. Right hand side vector means left hand side also a vector. Both the vector symbols should be used. Sometimes right hand side, for example, dv is equal to or f is equal to, they are vectors, bar can be done. On the right hand side, r square will be there, I will be there. So to show the vector nature, we have to select a unit vector. So all that becomes complicated. That's why it's better to avoid the vector equations unless it is very necessary. So here, just dB is proportional to the current element ideal. So more exactly speaking, dl bar. So it's in a more simpler way it can be shown as only ideal. So exactly means dl bar. So that will be a little complicated vector equation. So it's better to avoid that. Later, finally, it can be expressed in vector notation also. So now the important thing is, what about in between position? Why the magnetic induction decreases from maximum position, maximum value? Imagine that this point, all of them lie at the same distance. Then here on the perpendicular bisector it will be maximum, anywhere it will be lesser, and finally on the axis it will become 0. What's the reason? Reason is the vector nature of the elemental length. Now elemental length is nothing but, now elemental length, it appears a little strange why it's a vector. So immediately we have to go to the original thing, charge momentum. Now charge momentum is really producing this magnetic field or moving charge, or more simply considering the vector nature. So imagine reminding the vector nature of this moving charge as charge momentum dq into v bar. So that is actually producing this magnetic induction, because without motion, without velocity, no field will be possible. So in the perpendicular direction, we got the magnetic induction, and it has been found that it's actually proportional to the current element. So now, if you are taking this particular position, now this charge momentum can be resolved into, because it's a vector quantity, it can resolve into two components. So now call the angle, now, so whatever things we are seeing here are simple. Now this is the direction of the axis, direction is the direction of the elemental length. Now call the angle between the direction of the elemental length and the position vector of the point P, where we are trying to find out that field. Position vector of the point P with respect to the center of the element, which is denoted as R here. The angle between R and dl, or extension of dl, call the angle as simply theta. Now resolve the vector quantity here, the momentum, charge momentum vector, into two components. So one component, exactly, so whatever things we are seeing here are simple. So this is the element charge momentum here, which is in the direction of the axis. So now, or which is in the direction of dl, or elemental length dl. Now this vector quantity can be now resolved into, so this is the vector, actually I can, so we can just imagine the vector to be an arrow like this. So now this vector, so actually if I'm just saying it but without showing it, so I'll try to use a different color, which immediately I'll erase it. So this is the elemental length dl, it's a vector quantity. Now resolve this elemental length or charge momentum vector into two components. One component along this direction, this way, along the r, and the other component like this, one component this way. What will be this here? It will be the component at an angle theta, and the other component which is perpendicular to r. This way we can get two components. And what will be this component here? This component will be cos theta. The component of vector at an angle theta will be what? Cos theta. And this will be, so what is this vector now? Elemental length, ideal. And this component will be what? Ideal cos theta. And this component will be what? Ideal sin theta. Ideal sin theta. So this momentum vector, so which is the charge momentum vector, has two components. One is the component at an angle theta, that is along r, and the other is the perpendicular component to the r. So what is the perpendicular component here? The perpendicular component is very simple. What is the perpendicular component here? It is ideal sin theta. So ideal sin theta, which is actually, ideal is what? Charge momentum. So charge momentum produces a magnetic induction, we know, on its perpendicular bisector. So this point now is lying on the perpendicular bisector of ideal sin theta, but the point P lies on the what? Axis of the parallel component to R. That is, it's lying on the actual axis of the parallel component ideal cos theta. So because any point on the axis of any charge momentum or current element will be what? 0. Already we have seen that on the axis of the elemental length or current element, dB is 0. So now we have the current element, what here along R? It is ideal cos theta. So due to ideal cos theta, dB here will be 0. So whatever dB here we have at the point P, it's completely purely due to what? Ideal sin theta. That is the perpendicular component of the current element, or the perpendicular component of the charge momentum. That's the reason here. So now, so whatever things we are seeing here are simple. Nowhere any complication is there. So now I'm just directly using this here. So the magnetic induction here, dB at any point P, not on the perpendicular bisector of the elemental length dl here. Now ignore the yellow color things. We are using the yellow color diagram lines here or expression here only for the sake of understanding. Now the important thing is the elemental length blue here, actually, which is not visible now. I can just remove it just by deleting the yellow color which I have written. Wait seconds, fraction of a second I can delete it. But first important thing is what we got from this here. So the magnetic induction at the point P here is purely due to what? The perpendicular component of the current element ideal, that which is nothing but ideal sin theta, because the point P is lying on the perpendicular bisector of the component ideal sin theta, and it's lying on the axis of the parallel component ideal cos theta. So field can't be produced by the parallel component ideal cos theta. So already the magnetic induction, using simple methods, it is proved that the magnetic induction is exactly at any point on the perpendicular bisector of a current element is actually proportional, exactly proportional to ideal. So the magnetic induction here dB is what? It is due to the perpendicular component ideal sin theta. So directly it can now be said that the magnetic induction, so this is the first part of the Biot-Savart law. It's not complicated. Any doubt is there, just pause the video, you not listen to the video again, on your own you think about it. Within few seconds the entire answer will become clear, no complication anywhere. So the very first part of the magnetic induction, the Biot-Savart law, is the magnetic induction. See here, it's very simple. So once again, just check the here. This is the side heading. So we have the diagram here. Here actually the statement will be coming. So statement should be written here. Actually very little space is there, but still very easily a statement can be written. So it will be taking about 4 to 5 lines. So I leave some sufficient space. And here actually statement will be ending roughly here. So directly the very first part of the statement, a very simple manner it can be written. The magnetic induction due to the current carrying element dl is simply proportional to what? Ideal sin theta. So what is ideal sin theta? Ideal is the current element. It's actually the product of the current and the length of the element and the sine of the angle theta. What is coming? What is the proof for this? The proof we have seen using the components of the very simple vector, which is the charge momentum vector, which is nothing but current element, the product of current and the elemental length, treating elemental length as a vector. So this is the first part of the Biot-Savart law. And another very important thing is the magnetic induction at this point not just depends on ideal sin theta, it is also found to depend upon the distance r. So it is found that it is inversely proportional to the distance r square. That is exactly speaking, that is square of the distance r. So that means already this one roughly we can guess. So at more distance field will be definitely weaker. So as r increases, definitely field will be decreasing. So it has been found out that experimentally and also theoretically it has been found out that the magnetic induction is exactly inversely proportional to the square of the distance. So it's also an inverse square law exactly similar to the Coulomb's inverse square law in magnetism, the force between two magnetic poles. We have seen that it is inversely proportional to the square of the distance between the magnetic poles, and the Coulomb's inverse square law in electricity, inversely proportional to force, electrostatic force between two charges, inversely proportional to the square of the distance between the two electric charges. So exactly the same way, the second part of the Biot-Savart law simply states that it's inversely proportional to the square of the distance of the point from the center of the element. So these are the two simple parts of the Biot-Savart law. So now dB is proportional to this and dB is proportional to this. So dB should be proportional to this into this. So ideal sin theta into 1 by r square. So this now can be written as what? Ideal sin theta into 1 by r square is what? Ideal sin theta by r square. That way it can be written. So the magnetic induction, now it can be written as simply combining both the above parts. dV is proportional to ideal sin theta into 1 by r square is what? Ideal sin theta by r square, this way. So now, so the magnetic induction is coming to be proportional to this entire big, slightly big expression. So left is proportional to right. So left can be written as what? Constant into right. So dB is equal to some constant, proportionality constant into right. Now this proportionality constant, it can be taken as by any symbol, K or K1 or C1, anyway it can be taken. But now the important thing is magnetic induction is what? Force acting on a unit north pole. That's the basic definition of magnetic induction or magnetic field vector B. How is magnetic field vector B at any point in a magnetic field is defined? It is defined basically as a force acting on a, we have seen this firstly where in the lesson magnetism and magnetic properties of materials, force acting on a unit north pole, force per one unit north pole. That's how it has been defined. We have seen the expression also, but this is the way, simplest way in which it can be done. Force per unit north pole. And what is the electric field vector? Force per unit charge, unit positive charge. That's how electric field vector and magnetic field vectors have been defined. So how the force is measured on a unit north pole? How the force is measured on a positive charge? Force exerted by one charge on another charge is given by Coulomb's inverse square law in electricity. Like that, force exerted by one magnetic pole on another magnetic pole is given by the Coulomb's inverse square law in magnetism. Now, based on the Coulomb's inverse square law, this proportionality constant has been determined. Coulomb's inverse square law in magnetism. What is the proportionality constant in Coulomb's inverse square law in magnetism? Try to remember. The Coulomb's inverse square law in magnetism, the proportionality constant was, again I am writing another rough column, another simple factor we are just using here. The force between two magnetic poles whose pole strengths are S1 and S2. We have seen that it's proportional to the product of the pole strengths and inversely proportional to the square of the distance between the two magnetic poles. Just like Coulomb's inverse square law, let's take Q1 Q2 by R square. So in magnetism, the distance between two magnetic poles, strengths of the two poles are denoted as S1, S2, just like charges Q1, Q2. And the proportionality constant in Coulomb's inverse square law is what? 1 by 4 pi epsilon naught. In magnetism, the proportionality constant is what? Mu naught by 4 pi. So this is the Coulomb's inverse square law in magnetism. Try to remember. We already seen this in the previous lesson, immediate previous lesson. After current electricity, the lesson is what? Magnetism and magnetic properties of materials. After that, we have come to the lesson moving charges in magnetism, which is called as electromagnetism. So based on the Coulomb's inverse square law in magnetism, it has been proved that the proportionality constant is exactly the same as the proportionality constant in Coulomb's inverse square law. The proof of this partly we'll be seeing in the next topic. In the next topic, we'll be exactly seeing the similarity between a magnet producing a magnetic field, real magnet producing a magnetic field. Practically, we have seen magnets and their magnetic fields, how they apply magnetic fields and forces on magnetic materials and other magnets or other magnetic poles. So we can really see the similarity between a bar magnet or a magnet and a regular wire conductor carrying current, which also produces its own magnetic field. The similarities and many identical things, they are not real similar things, not roughly similar things, they are exact. Both are identical. The proofs will be coming. So in that partly the proof of this will be coming. So proportionality constant can be proved to be mu naught by 4 pi, which is same as the proportionality constant in the Coulomb's inverse square law in magnetism. So proportionality constant instead of K1, it's written as mu naught by 4 pi. After that, the remaining expression I'm writing as it is ideal sine theta by R square. So that's the thing. So this is the main form of the Biot-Savart's law. So it is very simple. Nowhere any complication is there. Very, very simple to remember. Very, very important. Very, very powerful. Many things in magnetism, they are actually derived or explained using this very simple Biot-Savart's law. But the thing is here also, just see here, observe carefully. dB is a vector. So its vector nature, strictly speaking, should be indicated by bar. But if a bar is indicated here, another right hand side also, its vector nature should be shown. So here right hand side becomes a little difficult to show the vector nature. Though many vectors are dl, we have seen that it's a vector. Roughly we have seen in the rough column the proof. Position vector also, r is also vector. In that form it should be written, or at least in the form of unit vector n cap, like that it should be written. To avoid such things, that is actually not shown here. But vector nature also, vector equation also will be useful, but very less useful. So finally this can be converted to vector equation also, but that also will not be complicated. In just one step or half step it can be obtained. So this is the first basic form of the Biot-Savart's law. So whatever things we are seeing here are simple. Nowhere any complication is there. Now just see here. Now the page, the time of this particular the particular diagram, try to remember. So just okay. So what I wanted to tell is, so here just see here. So we are getting the derivation steps actually from the components, but the components are actually in the final diagram. I have to remove all this yellow extra lines which I have drawn for the sake of understanding. I have to remove them. So the diagram again becomes same as the earlier diagram. Very simple diagram without any complicated things. So, but just remember the time is actually it's the 36th minute. So the yellow lines actually which show the components, they are very, very useful for the sake of understanding. So they can be, you can draw them just with a light pencil. So when you're taking that, so compulsorily every scientific derivation, especially the most important derivations of the syllabus from the board examination point of view, they are the real scientific derivations. No problem can compare with them, can be compared to them. So problems are just like skyscrapers, which humans can construct, but scientific derivations are like the Earth itself, like the planets itself. Every skyscraper, even a country, big mountains, big skyscrapers, natural mountains also just like look like points on a planet. or in the solar system or in the universe itself. They are nothing compared to scientific derivations. Scientific derivations are so powerful. They have lot of depth, lot of understanding, lot of applications. A problem will stop there only, or a few applications it can have. A very good problem, but still they are just like artificial, that is man-made skyscrapers. So real understanding will be there only in a scientific derivation. So always you have to be revising the derivation again and again, asking different questions. So every question answer will be directly based on very simple definitions and very simple laws. So such extra things useful for the understanding. So they must be not be disturbing the actual syllabus derivation. So they can be slightly written with a pencil so that the actual diagram will not get disturbed. So it's not possible to write this everything again. Already I have drawn DL here in the rough column. So to get the actual, which is the vector here, why it's resolved into components. Again, to draw this again here, it will become complicated. So here itself with a pencil it can be drawn. So any doubt is there, you can just think of them. Otherwise, just preparing for the exam or for the entrance problems, directly quickly the diagram and the equation can be revised. That's sufficient. So when more time is there, more different kinds of questions you want to ask and find out, then the pencil drawings will be helping. So I'll just quickly remove them when the notes has to be running notes has to be written. So this is the thing. Now the important thing is how to write this in vector notation. So whatever things we are seeing here are simple. Nowhere any complication is there. And what is mu naught called as? It's called as permeability of free space. Already we have seen this in magnetism. So this is the equation for Biot-Savart law, magnetic induction due to a current carrying element at any point near it. So this is only magnetic induction due to a small element. So it's a vector quantity, bar dB bar should be coming. So like that, then how to find out the magnetic induction due to the complete conductor? So at this point, dB due to this first element, you call it as dB1. Due to the second element, another element you take here, that you call it as dB2 at the same point. So every dB due to every element can be determined from this equation, and all of them integral dB bar. We have to add this, all the dBs, then we'll be getting the total field. So in that way, the magnetic induction due to a complete conductor also can be determined just using the same Biot-Savart law. So using this actually, even the complete infinite long straight current carrying conductor also total magnetic induction can be determined with the help of the Biot-Savart law. It has very wide applications. So that's why it is the almost the most important law in electromagnetism. Another law also exists, already I said at the beginning of this topic, Ampere's law. Certain situations that will be more useful. Certain situations Biot-Savart law will be more useful. And whatever Biot-Savart law so whatever topic can be derived using Biot-Savart law, actually using Ampere's law also it can be derived. They are said to be almost equivalent laws, but they appear to be completely different, but still they are said to be almost equivalent laws. So now how to express this in vector notation? Now just see here, left hand side there is no problem, dB bar, but right hand side just see here, there are already two vectors. One see here in the current element, just see here there is a current element or charge momentum, which is the vector here, dl bar. And what is the other vector here? R bar also can be taken as a vector, position vector of point P with respect to the center of the elemental length. So taking origin at the center of the element. So treating R as a vector, so really dl and R can be expressed in vector notation. And another very important thing is, what is the direction of the magnetic induction here? Now the direction of the magnetic induction, just see here, what is the direction of the magnetic induction? Magnetic induction direction will be always same as the direction of the magnetic line of force. So at this particular point on the circular line of force, if you draw a tangent, again I'll just use a different color. So the actual diagram, this is actual syllabus diagram of Earsted's experiment or Oersted's experiment. So I don't want to change that. Even in the rough column also, it's better not to change the syllabus diagrams because they were the real scientific diagrams. Even this is also not less scientific. This actually comes from the definition of magnetic induction, but still let both be not mixed. So this is the direction of magnetic induction, exactly tangential. So it can be seen that on the right hand side, it's directed somewhat forward. On the left hand side, magnetic induction will be directed somewhat backwards, that way. So now, due to the current element here, what is the direction of magnetic induction means? It can be seen that on the right hand side, it's directed exactly into the board, into the plane of the paper, into the plane of the screen here. For example, I'm drawing this on a board, blackboard, vertical blackboard. It's directed exactly perpendicular to the plane of the board on the right hand side of the current element. On the left hand side, it will be directed out of the plane. So it can be shown that using the same rule. What is the rule that is actually used here? What is the rule that is actually used here? The rule that is actually used here is the right hand corkscrew rule, like this. This is the right hand corkscrew rule. So imagine that a right hand corkscrew is held along the parallel to the conductor such that when it's turned, it should be advancing in the direction of the current, like this. That means in this direction the screw should be advancing. Then the direction of the rotation of the head will give the direction of the lines of force. That's the right hand corkscrew rule to get the direction of the lines of force. Or even the right hand thumb rule also can be used. We have seen that even right hand thumb rule also can be used. If the straight conductor is gripped in the right hand with the thumb pointing in the direction of the current, fingers curled around the conductor, then the direction of the curl of fingers will give the direction of the magnetic lines of force. Using the right hand thumb rule also, very easily the direction of the lines of force can be shown to be on the right hand side of the conductor. Here they will be directed in the forward direction. That means away from us. We are seeing the screen from this side, and on the left hand side they will be towards us, like that. So that way, using right hand thumb rule or even right hand corkscrew rule, the direction can be obtained. So so very easy right hand. So just check it once again. So we are just putting the here like this way. So here this way. Right hand corkscrew rule, and you're turning it in such a way that the corkscrew should be, how to turn it, in what direction should be turned, this way. So this side, so it's actually should be turned like this way. This way should be turned. So this side, right side of the head of the screw, this portion should be going into the plane of the paper, and this should be coming out of the plane of the paper. That way it should be turned for it to advance in the direction of the current. Then the direction of rotation of the screw or head of the screw will give the direction of the lines of force. So here a corkscrew can be imagined like this. So similar right hand corkscrew can be imagined here. Now we have to turn it in such a way that it should be advancing in this direction. So when it is turned like that, so I'm just putting it here. It's here along the current element DL. Here along the current element DL, I'm just putting it, or even along the perpendicular component ideal sine it also it can be put. So DL actually it's difficult to draw. I'll just draw it in this direction, in the direction of the ideal sine theta. This way I'm just putting. So I'll remove all the yellow color lines. So this way I'm putting. So it's very simple. This way. So now it's turned like this. So how to make it advance in the direction of the current, in this direction? Current is in this direction. It should be advancing in this direction. So it should be turned like this way. So this portion should be going into the plane of the paper, this end of the head of the screw. This end should be coming outside. It's actually difficult to show. So somewhat like this. So this is more easier, I think. Yes, this is more easier. That way it should be turned. This arrow it's better to follow. Like this it should be turned. So when it's turned like this, just see here on the right side of the element, that is on the right side of the screw, direction of rotation is into the board. So this way, into the screen like this. In this direction it's present. On the left side of the corkscrew, direction of rotation will be out of the screen. Out of the screen is always shown by, towards us is actually shown by a dot, away from us. So away from us, that means into the board, or treating this as a blackboard, or this is a screen, white screen, into the screen or into the board, it's actually shown by a cross. Because an arrow which is actually shot into the board, only feathers can be seen. Arrow which is coming out of the board, only we can see the point tip. So thus it can be seen that the magnetic induction here due to the current element is directed perpendicular to the board. What is the plane of the board now? Plane of the board is a plane containing current element DL and R. So DL is a vector, DL is a vector, DL bar. R is also, you can treat as, it's treated as a vector, position vector R bar. So DB bar is a vector whose direction is perpendicular to the plane containing DL bar and R bar. That's the thing. As given by what? As given by the right hand corkscrew rule, or even the right hand thumb rule. Right hand thumb rule is more difficult to draw, so I'm not drawing the right hand thumb rule. So if you want to use right hand thumb rule also, we can just use here. The same thing can be applied here also. So one method is sufficient. Right hand corkscrew rule, we are getting the answer. So this is the direction of the magnetic induction. So it's better if you practice to get the direction dB using right hand thumb rule also. Just imagine that this conductor, elemental length. Again, you take this component, only perpendicular component. Imagine that it's gripped in the right hand. with the thumb pointing. So this entire elemental length, ideal sine theta, imagine that it's gripped in the right hand with thumb pointing this direction. Direction of curl of fingers will be on this side, it will be into the board. On the left hand side, it will be out of the board. So that way also we can get, no problem. It's better to just for the sake of revision. So sharpness of the brain, you can just revise both the laws. Both laws we can get the answer. So this is the direction of magnetic induction. Now coming back to the actual derivation. So what are the vectors here? dl is a vector, r is a vector. Now multiply, I'll just multiply numerator and denominator with r so that in the numerator both the vectors will be present, dl and r will be present. Then what will happen is, so db now can be written as very simply. So db is equal to, just observe here, ideal, so mu naught by 4 pi, I'm writing as it is, entire expression, ideal sine theta, just see here, ideal sine theta. Ideal, numerator and denominator, I want to bring r to this side so that both the vectors will be present in the numerator itself. So now vector natures, because of their vector natures, bars can also be used both on the left hand side and right hand side. For that purpose, r should be brought here. So I'm multiplying numerator and denominator with r. So then it will become what? I dl r sine theta by, already r square is there, denominator again with multiplied with r means it will become r cube. Now just observe here, this is very important. So in this dl is a vector, r is a vector, and theta is what? Dl vector is what? This is the direction of dl vector, this direction along the axis dashed line here, and r vector is what? In this direction. So vector nature, how to show? Bar should, that is arrow should be shown. So r being a vector, arrow can be shown here, but that becomes, makes the figure even more congested, too many things. dl vector, so though I'm not showing it as dl bar, but still direction of current is there. That is the direction of dl vector, because direction of current is nothing but direction of the velocity in the charge momentum, dq into v, already we have seen. So that's the direction of velocity direction and elemental length direction are same. Elemental length direction, velocity direction is same as direction of the current itself. That's the direction of motion of the charge. So already we know. So theta is the angle between really the elemental, the vectors dl and r vectors. So the product of two vectors and the sign of the angle theta between them is what? Cross product of the two vectors. So this is really what? dlr sin theta is actually really the magnitude of the cross product of two vectors. Magnitude of the cross product of two vectors. So whatever things we are seeing here are simple, nowhere any complication is there. Now in order to write this in vector notation, now I'll do one thing. What is the direction of dv bar? We know it's directed into the plane of the screen here. That means it's directed into the plane containing dl and r bar vector. In the direction of dv bar vector, I'll just imagine a, so say n cap, a unit normal like this I want to write with, because I in the direction of dv bar, I'm just putting a unit normal vector n cap this way, it can be written. So this n cap, so this, if possible, I'll just eliminate this also, because diagram should be as simple as possible. Otherwise I'll keep n cap as it is. If it has to be kept, I'll just put it in mark, just make it blue color. So all the yellow colors I'll just remove everything, because the screw, right hand corkscrew, all this is for the sake of applying the laws to get the required direction and to get the required steps. So all the yellow colors, I'll just remove everything, most of the things, so that as simple as possible the notes will be finally there. So now I'll just write this in vector notation, very easy manner it can be written. See here, so this now can be written as db is equal to, so just see here, very simple step, db is equal to mu naught by 4 pi, vector nature db bar is equal to the mu naught by 4 pi I into dl. Okay, just a moment please. See here, ideal into r sin theta. So whatever things we are seeing here are simple, nowhere any complication is there. So I'll just write it more clearly, just a moment. So I into dlr sin theta, so dl into r into, so small space is better to maintain, dl into r, because they are separate, otherwise it looks like dlr, dealers, so some other word, short form of word like that, it looks like a complete word, it doesn't look like a mathematical multiplication. So dl into r into sin theta divided by r cube. Now any vector can be written as, just see here, any vector can be written as dv bar is a vector. We know its magnitude. Equation 1, result 1, Roman 1 gives the magnitude of dv. So any vector can be written as its magnitude into its unit vector. So what is the unit vector of dv bar? Unit vector of dv bar means a unit vector in the direction of dv bar, which is also directed into the plane of the board. So this can be written as its magnitude into n cap. So now this can be written as into n cap. It can be written into n cap. Now just observe here. So here this dl r sin theta, dl into r into sin theta, it's actually the magnitude of the cross product of dl and r vectors, dl bar and r bar vectors. But what is the direction of dl bar and r bar? So we know how to get the direction of dl bar and r bar. So dl bar is this vector here from here to here. So now I'll just make dl bar like original diagram. This is the dl bar vector. I said I'll remove the yellow color. So this is the original DL bar, which actually was not visible till, so now actually little 1 minute before also it was not visible because of the yellow color additions, vector components. So DL bar is this direction, in the direction of this dashed line, which is actually the axis of the DL bar. So now DL bar is this vector in this direction, in the direction of this yellow arrow upwards, and R bar is in this direction, in the direction of this small yellow arrow towards P. So dl bar cross r bar, cross product of two vectors, again from the right hand Corkscrew rule. Its direction is given by the right hand Corkscrew rule. So if right hand Corkscrew is actually used here, so whatever things we are seeing here are simple, nowhere any complication is there. Now what is right hand Corkscrew rule? Just try to check how to obtain the cross product of two vectors. This just check here. I'm just drawing another rough column. Actually there is no place here to draw the rough column. So I'll draw a rough column here. All the rough columns I'll keep in the final running notes also. You have two vectors here. A bar is one vector. So B bar is another vector. So angle between them is theta. So the two vectors are belong to a particular plane. They lie in a particular plane. Now the cross product of these two vectors, by the definition of cross product, so always any doubt comes in science and technology or science and engineering, any doubt comes related to any step, always what will help is the definitions, very simple definitions. A definition is nothing but the formation of a sentence which completely gives the full 100% meaning of a particular quantity or a particular process. That's called as definition or scientific definition. A scientific definition will be very, very in simplest possible words. Nothing can be more simpler than that. But using that, most complicated things, any complicated things of any complication can be understood very clearly. So cross product of two vectors is a vector which is perpendicular to the plane containing the given two vectors, perpendicular exactly, making angle 90 degrees with both the vectors a bar and b bar. Its magnitude is ab sin theta and its direction is exactly given by the right hand thumb rule or right hand Corkscrew rule. So if what is that right hand Corkscrew rule, also try to remember. I'm just explaining this because always along with the full definition must be revised. What is right hand Corkscrew rule? Imagine a right-handed corkscrew placed perpendicular to the plane containing the given two vectors a bar and b bar, and imagine that it's rotated in what direction? From the first vector to the second vector. First vector in this direction. It should be rotated from the first vector to the second vector. In this direction it should be rotated. First vector a bar to b bar. So when it's rotated like that, in whatever direction it advances, we can just see that right-hand corkscrew once it's rotated like this, putting it perpendicular to this like this. The same diagram you can just imagine to be placed here. When it's rotated from here to here in this direction, it actually advances upwards. That gives the direction of A cross B. So that same thing can be applied here. So imagine right-handed Corkscrew rule. What is the best way to remember? But how should it be placed? Perpendicular to the plane containing this and this. So we can't draw this. If it's placed perpendicularly, from the top if we see, we can just see only the tip. Tip because it's very small. We can just say around the tip, we can just see the head also. Like this it looks like. Right-handed Corkscrew rule. So head, this is the head. At the center tip will be visible from the top if we see. That way it's placed perpendicular to the plane. Now you rotate, imagine that it's rotated from dl to r, first vector to the second vector. dl to r, first vector to second vector. And in what direction it advances? It advances perpendicular to the plane, downwards, into the plane of the board, in the direction. So we can just see that even dl cross r also, it is directed into the plane. So n cap, like this, exactly in the direction of dv bar. So n cap is not just the unit vector in the direction of dvb, it's also unit vector in the direction of dl cross r also. So now just see here, see that very simple thing. From the definition of cross product, this is the magnitude of the cross product and the unit vector of the cross product. So magnitude into unit vector will give the complete vector. What is the complete vector here? dl cross r. So it's very simple, you see, in just one word. I'm not using more words. Just one single phrase I'm using. So magnitude of the vector into its unit vector is nothing but the complete vector cross product dl cross r. So now vector notation is fully coming. mu naught by 4 pi I into what is the vector notation? Very simple, dl cross r. dl r and magnitude into its unit vector is what? Dl cross r by r cube. So this is the right hand full vector. But just see, always vector equations are complicated. Nothing can be made out from the equation. They are said to be in physics and also in engineering. They are said to be the most useless equations. Nothing will be visible. So what is dl cross r? Actually, it has a meaning. The definition of cross product, the basic definition of cross product has to be, it has a meaning, deep meaning it has, but that meaning will not be visible. That's why most of the engineering subjects vector equations are actually skipped off. Everything is written like the equation 1. This is called as result 2. Just remember this, vector equations, they are called as account books. So in many people, many scientists call the vector equations as account books. So nothing can be made out of. So the best way to understand is a particular concept is using the scalar equations. Even they also, many scientists say that even they also can be understood, but a lot of effort, the definition again and again, the definition of cross product should be applied. Original definitions, not just the definition which we are saying. Cross product of two vectors is the product of the magnitudes of the, you see here the cross product of two vectors, product of the magnitudes of the two vectors and the sine of the angle theta. So this is only rough meaning. It's also just like a account keeping, something like that. It's called as sum by different scientists. So vector equations, better to avoid completely. So any meaning, always any complication, the first equation itself can solve. Certain things become too much complicated, certain situations, then the vector equation also will be coming. Then this actually will take 100 steps, means vector equation will give the answer in just 2 steps. But that also, the meaning can't be grasped quickly unless the definitions are applied again and again. In the 2 steps, if you apply the definition 50 to 100 times, you have to apply. It will take a lot of time. So brain will be actually completely, it will get exhausted. But still, without thinking also, just like a computer, we can use this equation. Computer, it has its own thinking, but we'll get the answer. Like that, this equation, second equation will be useful. So this is the taken as the final form, but less important. So actually I have to call this as equation 2. There's no place here. Later I'll just move the equation. I can actually move the equation leftwards and put the right hand side will get some space, then I'll call it as equation 2. That's the final equation. So the direction of dB is perpendicular to the plane containing dl and r, the two vectors dl and r. That's the final thing. So this is the complete Biot-Savart's law. Nowhere any complication is there, everything is simple. Now the thing is how to fill up this statement. 6 lines already I said it will be coming, so I have to remove all the yellow color things. Now the thing is here again, just remember this is what just see here, this is the minute is actually, time is actually most probably the 51st minute, I think 51 or 52, later you just check it. This 52nd minute you take a snapshot so that the pencil things, whatever things you think they'll be useful later when you are reading the answer. Because I'll remove all the things and I'll just keep this very simple fair diagram without the yellow arrows here, the component arrows. So this I'll put a keep n cap, I'll put keep this dv bar also is very important direction. Cross denotes it's directed perpendicularly into the plane of the screen. So that I'll put, everything else I'll remove. Even the here this here right hand Corkscrew also, one of them I'll have to remove to make the diagram simple. So everything else I'll keep, and in the gaps I'll just fill up the matter. Here statement will be coming, here just 2-3 lines explanation will be coming actually here, 2 or 3 lines explanation. After that derivation will be as it is, the steps will be coming here, just 1 or 2 lines, that's all, entire derivation. So to write this actually it will take only 2 minutes to write the running notes. So in the next so immediately I'll just display the running notes. I'll not explain all the how to write. So according to Biot-Savart, like that statement will be coming. The magnetic induction dB due to current carrying element dl is directly proportional to the strength of the current I. The length of the, like that the statement entirely will be coming, but I'll not show that in the video directly. The final output I'll be showing. All the equations will be remaining as it is. With small, I'll just move the equation this a little to the left or right, but such that some sufficient space comes to write the 3 lines. That way I'm just showing it. So quickly copy down the entire derivation running notes. Don't take the scientific derivations lightly. And even more important than the derivation are the rough columns. Many things are there in the rough columns. This also I'll keep put as it is, but more neatly, because all the other extra diagrams I'm just removing, it will be more clear. So take out the rough columns, they are more important, and then the running notes, and then attend the next topic. So this is the actual complete running notes of the topic. So now quickly take down the entire running notes. So I have removed most of the explanatory yellow color lines, vector components, etc. So this is the simplest possible, very simple diagram. So entire derivation is as it is. The only thing is between the derivation steps, the matter has to be written. That I have completed. So quickly take down the entire running notes. So actually, left side one page is there, right side one page. Beyond this, on the left and right side of the thick line. So this rough column actually belongs to the first page. Actually, the entire rough column should be taken here itself. This is the first page, rough column. The entire rough column, most of the rough column, 90%. So only this top portion actually belongs to the second page actually. So this right side is the second page, and the derivation actually almost is ending at the second equation. So but below that a small thing should be written. So what is to be written, I'm just showing here. So quickly take down this. So this particular minute, most probably it is 69th or 70th minute. So put the video to a pause, take the screenshot and write the entire rough column. And after this, one more sentence is there. So that sentence I'm just showing it. So this is the sentence actually. So this is the completion of the answer. After this, the line actually denotes the completion of the answer, where the direction of dB is perpendicular to the plane containing dl and r. That's all. This is the completion. So quickly take down this before attending the next class.